The neuron. This curious little cell within the human nervous system is able to receive information, process it, and communicate it to others like it, which isn't unique. Other types of cells can do that too. But when this neuron is grouped together with other neurons, over 80 billion in the human brain, via the contact points called synapses, sending and receiving electrochemical signals, something extraordinary happens: the human experience. Whether it's experiencing the bliss of falling in love or the bitter feeling of losing a friend, all of it arises from this incredibly complex web of interconnections. One of the most important questions of our century then is, how? Hello world, it's Siraj, and I wrote a paper. It's titled The Neural Qubit, where I demonstrate a novel pipeline training a newer machine learning technique called the quantum variational circuit on a Kaggle dataset to detect fraudulent credit card transactions. In this episode, I want to explain my motivations, how I wrote the paper, what I learned, and most importantly, discuss what the novel business applications of this technology could be. Let's start with my motivations. I'm frustrated that we're not seeing enough radically unique research directions. Instead, we're seeing incremental improvements on existing architectures to achieve scores that are a few points higher on a variety of standard tests. We have added a new layer. Francois Chollet, a prominent AI researcher at Google and author of the deep learning library Keras, shares my sentiment. He recently tweeted that, "I guarantee you that the dominant AI algorithm of the 2050s will not be a stack of differentiable layers trained with stochastic gradient descent." For context, he's talking about modern deep learning, the hottest subfield of AI, which involves repeatedly chaining math operations together that are applied to a dataset and optimized using a technique called gradient descent. If we're going to create even more intelligent systems, we need to reconsider some of our most basic assumptions about the nature of intelligence itself. Brian Johnson recommended the book The Biography of Zero on my podcast, which demonstrates why this is important. Check it out.
Zero represented this blind spot in history, and without zero, you can't do modern engineering, you can't build computers, you can't do anything we do really in the world today. And the discovery of zero was very difficult because it clashed with religious frameworks and with just the observation of why would zero even be useful. And so, for example, in the West, it clashed with Christianity because the void or nothingness was not something that philosophically, theologically was interesting. But in the East, they embraced this infinite and nothingness.
As humans, we have over 188 cognitive biases built into our brains, and we're often limited by them subconsciously from seeing things from a different frame. D-Wave, a quantum computing company and one of my clients, invited me to see their quantum computer in Vancouver many months ago, which sparked my interest in quantum computing and ways we could use it to accelerate innovation in AI. So I bought Richard Feynman's lectures on physics. Classical mechanics made a lot of sense. It describes the macroscopic scale, but quantum mechanics, not so much. It describes the microscopic scale. I guess I'm not alone in my confusion. Einstein once famously stated that quantum entanglement is spooky action at a distance. So against my own materialist bias, I started reading mystical texts from the East, hoping that maybe some of these concepts could help me understand quantum mechanics better. What shocked me was that I learned that many of the founding fathers of quantum mechanics followed a similar trajectory. Heisenberg, for example, said that after the conversations about Indian philosophy, some of the ideas of quantum physics that had seemed so crazy suddenly made much more sense. Schrödinger said that Vedanta teaches that consciousness is singular. All happenings are played out in one universal consciousness, and there is no multiplicity of selves. I started questioning my own long-held beliefs that consciousness arises from matter. What if it's the other way around? What if it's matter that arises from consciousness, and that everything we see around us is an illusion? And if that is the case, can we build new technologies around that idea? But after doing some research into modern neuroscience and quantum mechanics literature, I realized I can't create a mathematical proof of a universal consciousness. We just don't yet have the tools to empirically, rigorously prove that belief. We don't have the right types of sensors. We don't have a proper theory of quantum gravity, and our knowledge of computational neuroscience is incredibly limited. We don't even have a way of quantifying consciousness. There are some studies by physicists like Sir Roger Penrose and Dr. John Hagelin that attempt to prove a universal consciousness, but they are largely viewed as lacking in the reproducibility of their results by the physics community and, frankly, myself. But that's okay. Science is awesome like that. I understand the female mind. Math, or it didn't happen. So I ended up omitting the word consciousness entirely from my paper, even though I wanted to, but did come to some interesting conclusions anyway about how, given some recent compelling evidence that quantum computation occurs in the brain, we can replicate that in machines programmatically. Our brain's neural networks are what inspired the advent of digital neural networks more than 50 years ago, but I use the term inspired loosely here. Human neurons both send and receive data in analog frequencies consisting of combinations and even overlays of tones, chirps, and strobes. The symbology of these transmissions are unique for each person, like a fingerprint. These frequencies can ride each other over a synapse and dendrite, so that one message might reach a target while another is shunted to another area. These behaviors constantly change as the city of activity inside the neuron are all making their own decisions about how to process these signals. Digital neural networks, however, have no corollary for this kind of signal processing complexity. One of the simplest types of neural networks, the perceptron, receives two floating point numbers and performs a multiplication operation between the two, then adds a bias value, and if the result passed through the activation function trips the minimum value, it sends it along either a Boolean or a numerical output. Despite this huge difference between the neuron in biology and the neuron in silicon, neural networks are still capable of performing incredibly challenging tasks, like image captioning, essay writing, and even driving cars. But they do have their limits, like, where's my robot girlfriend? For example, they can't yet perform causal reasoning, meaning making connections between disparate concepts. GPT-2 might generate a very compelling essay, but it doesn't understand what the concepts it's writing about are or how they're related. It's repeatedly making likely next word predictions using a probability model. Self-driving cars use neural networks for computer vision, but are still vulnerable to adversarial attacks, which can sometimes make them misclassify an image if a single pixel is replaced. So how do we improve these inefficiencies? We need better algorithms and more computational power. In my paper, I argue that quantum hardware and software can help us do both. They can allow us to solve problems of enormous time complexity in a feasible time span. If we can simulate our universe on a machine, chemical, physical, and biological interactions, we can build a simulated lab in the cloud that scales, ushering in a new era of scientific research for anyone to make discoveries using just their computer. And if we incorporate quantum computing into machine learning to get higher accuracy scores, that'll enable entrepreneurs to create more efficient services for every industry, from agriculture to finance. That's considered quantum supremacy, the potential ability of a quantum computing device to solve problems that classical computers practically can't, which tech companies like Google and D-Wave are racing towards. And there's recent compelling evidence that the human brain has quantum supremacy, theorized by Dr. Matt Fisher, a professor of physics at UC Santa Barbara. Before we get into his research, let's define two concepts from quantum mechanics: superposition and entanglement. At the quantum scale, particles can exist across all possible states simultaneously. This is known as a superposition of states. An electron, for example, may exist in two possible spin states, usually referred to as spin up and spin down, simultaneously, which tends to be difficult for us to be able to conceptualize since there's no corollary of that which we can observe. In fact, once a measurement of a particle is made, either by a device or a human, this superposition is lost, and we now have a particle in one known state. It gets more interesting though. When groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the state of the others, even when the particles are separated by a large distance, that's called entanglement. Quantum computers leverage these phenomena. While a classical computer uses bits to perform computation, a quantum machine uses qubits. Instead of taking on the value of either a 0 or a 1, it can take on both at the same time in a superimposed state. And these qubits can be entangled with each other to perform computations. But does the brain leverage these phenomena too? Max Tegmark, a physicist at MIT with a nice smile, argued that it doesn't in his 1999 paper, The Importance of Quantum Decoherence in Brain Processes. Quantum mechanics processes only continue to show their effects when the relevant information doesn't leak into the environment, also called decoherence. His argument was that decoherence timescales take place over a time of the order of 10 to the negative 13th to 10 to the negative 20th seconds. But the timescales over which neurons fire is different. It's 0.001 to 0.1 seconds, meaning it must be a classical computer. But Dr. Fisher more recently wrote that there's a loophole in that argument. Yes, quantum computation would indeed require isolation from the thermal bath of the human brain, but that's what nuclear spins are for. Because it is a charged particle in motion, i.e. spinning, an atomic nucleus creates a magnetic field. The north pole of this spin-generated magnetic field points at a certain direction in space. The nuclear spin state is the orientation of the spin-generated magnetic field relative to an external magnetic field. He proposed that there must be a common biological element with a very isolated nuclear spin inside of the brain that can serve as a kind of neural qubit. He calculated that it would have to be an atom with a nuclear spin of 1/2 to be able to maintain quantum coherence. And he found that there's only one that does so, phosphorus. Specifically, its only stable isotope, phosphorus 31, the only possible neural qubit, which when entangled with others like it, can maintain quantum coherence for up to 106 seconds. That's exciting, and there's much more research to be done here, but given this evidence, how would this change how we humans compute things? Glad you asked. Let's look at a simple coin toss example. Tossing a coin could land on heads or tails. In classical theory, we can represent this by a state with binary choices, H and T, each with a 1/2 probability. But in quantum theory, we can represent this coin tossing with a quantum bit. We can use a Bloch sphere to represent this quantum bit. It's a geometrical representation of the pure state space of a qubit. Every point on the Bloch sphere is a possible state of the qubit. Every point on the equator unit circle of the Bloch sphere represents a possible state of fair coin tossing. So tossing a fair coin can be represented equally well by these two states. These representations are called wave functions, and these coefficients are complex numbers whose modulus squared represents a corresponding probability. Basically, the resulting states can be translated to the coin is at a superposition state of heads and tails at the same time. It's like being a Lisp programmer, but also not being a Lisp programmer. Don't put that on your resume. So given the possibility of quantum computation in the brain, how can we translate it programmatically to neural networks? Quantum deep learning theory literature is vast. It involves lots and lots of new concepts that correspond to the classical concepts of neural network theory. Let's pick one, the variational circuit, the quantum analog to feed-forward neural networks. Variational circuits are a family of hybrid quantum classical algorithms. At the core of the algorithm is a quantum circuit, U, which depends on a set of circuit parameters, theta, as well as an objective function which defines a score for each set of parameters. Quantum algorithms work by applying quantum operations, called quantum gates, on subsets of qubits. Quantum gates are analogous to instructions in a classical program. A quantum algorithm represented using gates is called a quantum circuit. The goal is to optimize or train the circuit with respect to the objective function using, say, gradient descent. when applied to a classification task of fraud detection using a Kaggle dataset, I got a pretty good accuracy score. Not state of the art, but that's pretty cool considering this network leverages quantum effects on a simulated quantum environment. There are 3 things to remember from this video. There is evidence of quantum computation in neurons arising from the unique properties of phosphorus atoms. Quantum computing may soon offer possibilities to solve very complex problems much faster. And the variational circuit is the quantum analog of feed-forward neural networks. I believe that we'll someday have the technology to fully harness our reality and consciousness, whatever it is, to do unimaginably amazing things. And while science has done so much for us, it gives me no reason to believe that. But that's okay, because sometimes you gotta have a little faith.